Sorry if I seem a little hoarse tonight. I'm just getting over a cold, and hopefully my voice will hold out for the entire presentation. The Sudbury Mining District is one of the most important in the world, and the title of this topic tonight is an unearthly earthly metal-rich anomaly. Anomaly being something different, something special in the world. It's one of the most metal-rich places in the world, and I'll give you more details on that in a while. That's the earthly part of it. The unearthly part is the reason it's here, and we'll get into that a little bit more as well. But first, a little background. I'll refer to the Sudbury Mining District or Sudbury Basin. That's the whole area of the Sudbury area, including the metallurgical mining facilities and other important features of the area. The Sudbury structure is the entire geological structure that hosts all the different deposits and geological structures of the area. And the Sudbury Igneous Complex is the actual igneous complex that hosts the ore bodies. Hopefully some of these things will become more apparent as we go on. It wasn't always an important area. 150 or so years ago, it was just an area that was pristine wilderness. It was occupied by the Ojibwe people. There was some logging, trapping, subsistence living. It was pretty primitive and remote. The mineral interest started around 1856. This is before Canada was even a country, but I think probably the Upper Canada, as the province of Upper Canada was called, which is mostly Ontario. In those days, they were running meridians to getting ready for settlers and various other things to happen throughout the Upper Canada. And a land surveyor, while running the meridian, saw a strong deflection of his compass needle. As a matter of fact, he couldn't use his compass in a certain area, which was, of course, we now know Sudbury. That anomaly was mentioned to the Geological Survey of Canada, which had only been formed a few years previously, I think in 1846 or 1847. The GSC went and checked it out, and disappointingly only found low-grade rocks that had 2 or 3% copper, 1-2% nickel. And in those days, technology being what it was, that was really not of interest to anybody. The deposits were just too low. Nowadays, those would be great deposits for open pit mining. You could really make good money at those with modern technology. And they do. Anyway, in Ontario at the time, we were hewers of wood and drawers of water, and there were very few people who knew or cared anything about mining or minerals, and the anomaly and this low-grade mineralization was ignored, unexplored, and forgotten. In 1867, I'm sure all of you in the audience know, that's when Canada was established as a country. One of the first things that was done to try and unite Canada from east to west and try and offset the huge north-south bias that was present in many of the colonies across what became Canada. A railway was decided to develop a trans-Canada railway right from coast to coast to unite Canada. And that's what they undertook. When they were blasting the right-of-way in the area that we now know Sudbury, they found very dense sulfides, rusty sulfidey rock that seemed very rich in minerals. They weren't sure what at the time, but a number of people, some of the names which became famous, like Froude and Totten, Stobie, Crean, they staked claims, and eventually mines were developed on many of those properties. This is one of them. You saw those two names, Frood-Stobie. The Frood-Stobie mine, you can see it in the distance there. It dominated the skyline of eastern Sudbury for many, many, many decades, really for 100 years or more. It's finished now, but the Frood-Stobie complex was in fact the richest metal producing mine in the world. And as far as I know, there's no other mine that is single mine that's produced as much wealth as the Frood-Stobie mine. That head frame is torn down now, by the way. But back to the beginning. Americans were very helpful in the early days. Samuel Ritchie, an industrialist from Ohio, developed the Canadian Copper Company. And in those days, that was around the time that the electrification of North America was happening. So people were very, very interested in copper deposits, of which these weren't really copper deposits. They're really nickel with a little copper. However, they developed them to mine what copper they could. And the nickel was really a nuisance, a metallurgical nuisance. I think many of you know of the name that was Kupfer nickel or devil's nickel that was given to nickel in Germany a long time ago because it interfered metallurgically with the good minerals. Anyway, Mr. Ritchie shipped his ores to the Orford Refinery Company in New Jersey, and that's how things got started. A little later, a decade or two later, the world figured out that nickel iron alloys were extremely hard and tough and were great for armaments, which were becoming more and more important. And I guess you could say, fortunately or unfortunately, the early success of Sudbury was linked to the manufacture of armaments. World War I and World War II were hugely formative times for Sudbury. After the wars, stainless steel was the main thing that drove production at Sudbury. But again, we're getting ahead of ourselves. Again, back to the electrification of North America, Thomas Edison purchased deposits at Falconbridge, but he just couldn't, he really didn't know what to do with the nickel, and they weren't good enough for copper for his purposes. Eventually, he gave up and went away, and his deposits were taken over by other people. The Canadian Copper Company merged with Orford International Nickel Company, Orford, to make the International Nickel Company. And then later, the Mond Nickel Company from England formed a company, the Mond Nickel Company, to mine deposits at Garson, Victoria, and Levack, to supply their metallurgical facilities in Wales, which still happens to some extent. The big refinery in Wales still refines nickel. Eventually, Mond merged with International Nickel Company to form the International Nickel Company of Canada, which was the nickel colossus of the world. And for a number of decades, the International Nickel Company, or INCO, controlled the nickel market. Thayer Lindsley, another American entrepreneur who became legendary in Canada and well loved, he formed Falconbridge Mines, which had another big part of the Sudbury Basin, and he formed and mined nickel and copper there for many years. And formed Falconbridge became a gigantic company like Inco, based on a lot of the wealth that was generated from Sudbury. None of those mining companies exist anymore. Falconbridge eventually became bought up by Gencor Xstrata, the gigantic Swiss-based mining metals company. Inco was bought up by Vale, the gigantic Brazilian mining company. Some of Inco's properties were spun off to a small Canadian company, and even that was eventually swallowed by KGHM, a gigantic Polish-based copper miner. Only one little dinky company, which is the tiniest company, Walbridge Mining, still exists as a Canadian company, and they mined the tiny little Broken Hammer mine, which resulted in some spectacular Sperrylite specimens. And we'll see more about that later on. So demand, just a little postscript about commercial mining in Sudbury. Demand for nickel is much larger than Sudbury could ever supply. And so now there's gigantic lateritic nickel deposits, nickel oxide deposits around the world have made Sudbury much less important than it used to be. It's still an important producer, but it's only produces a fraction of the nickel. Giant lateritic deposits really now are the biggest producers. My history in Sudbury goes way back to 1975. I had my second summer job. I worked in the engineering department at the Levack mine, and there's me with I think a snoot full of Southern Comfort fishing on the Vermilion River, and that's the bunkhouse I stayed in for a summer for several months, and it's gone now, torn down. This is what I'm talking about, the immense wealth produced from Sudbury. Look at the billions of pounds of nickel and copper. Gold and silver have been considered kind of a byproduct, yet they produced more than most other mining camps that are specifically mined for gold and silver. The current value of the production is about $600 billion. I thought this was the richest place in the world. My original name of my talk was the most metal-rich place in the world. However, upon doing research, I found that certain other geological structures have surpassed Sudbury, like the Bushveld complex in South Africa, where they mine very high-value platinum. Norilsk, similar mineralogy to Sudbury, but very rich in platinum group metals, and the Witwatersrand, again, platinum group metals. Sudbury produces a lot of platinum group metals, but it's really a Sudbury, a nickel copper mining place with those as byproducts. So let's get to the interesting stuff. Geologically, people always thought it was some kind of big intrusive called the Lopalith that had nickel-rich magmas. But people started noticing certain things about the structure. And in the 60s, a fellow by the name of Dietz theorized that, in fact, the Sudbury structure was formed by a meteorite impacting the Earth. And he thought that it breached the crust, which caused these nickel-rich magmas to come out into the structure. He was close, but he wasn't really correct. Other workers followed and came up with better solutions. But in fact, he was right, basically right. The Sudbury structure is the result of a bolide impact 1.85 billion years ago. This bolide was a meteorite or a comet about 10 to 15 kilometers in diameter. And that's one big rock slamming into the Earth with unimaginable energy and impact. That's what caused the Sudbury impact structure. So if you look at this sketch by Mr. O'Dale, who seems to have it just right, you can see the meteorite impact or the bolide impact. And the key here is this. This is when it impacted, it formed a giant melt sheet. The rock melted underneath the impact of the bolide. And of course, the rock shattered underneath it. And when anytime you have a giant thing like this hitting the Earth, you get kind of a splash of rock and dust going up in the air, and a lot of it falling back into the structure, but the lighter stuff flying out and being ejected, and dust spreading out in the atmosphere. They figure that, in fact, at the time, the impact happened in a shallow sea because of the sediments that were later deposited on top of this crater. They figure that it had to be under a shallow sea. The plot thickens. So this is what the crater looked like for a while. It was underwater. The fallback ejecta, sediments formed on top of the fallback ejecta. Here's the melt rock, and here's the fractured shock zone underneath. We'll talk a little bit more about each of these features. This happened back in the Proterozoic era. The original crater was felt to be 200 to 250 kilometers across, which, as far as we know, is the third largest such crater in the world. There's a bigger one in South Africa, I think, and a bigger one in Mexico. The brecciation around that 200 to 250 kilometers, the brecciation, the shattering, was up to 80 kilometers away from the edges of the Sudbury impact structure. That's some force. Now, as I mentioned, there's other big bolide impacts, meteorite impacts in the world, and they don't all have big metal deposits in them. The rock that melted seemed to be rich in metals. And there's a possibility that some kind of big ultramafic or mafic intrusion that had those kind of metals in it was, in fact, just in the trajectory of the in the Earth at the source of impact. Maybe that's why. They're still not sure why, but that's one of the good ideas, is why where the source of the metals was, because it wasn't from the country rock. As I mentioned, the impact would have been pretty catastrophic, with debris thrown, they figure 800 kilometers or so, what they know about similar impacts. The dust would have been dispersed globally and would have caused some pretty nice sunsets. They've calculated that impact melt measured about 31,000 cubic kilometers of melted rock. That's a lot of melted rock, and would take quite a while to cool in those circumstances. So when it was molten, it differentiated with the heavier metals sinking down. The immiscible metals that we're interested in were deposited in basements, in cracks and big fissures and hollowed out areas, bigger areas of the crater walls. And those are the ore bodies that we're mining today. Now, there were two periods of mountain building and a lot of erosion. Think of the time frame here. This is one of the times where geological time implications really come home to roost. This happened 1.85 billion years ago. And since then, there's been mountains built and eroded to a depth of about 4 kilometers. So I'll show you a little bit more about that in a minute. Some of the things that tipped off earlier workers, they started finding these shatter cones in the rock all around the circumference for miles around the Sudbury structure, were these cone-shaped shatter marks in the rock, as you might imagine you'd have if something giant shattered a piece of rock. You get radial shock fractures. As well, when they diamond drilled underneath the Sudbury structure, they found very, very deep layers of solidified breccia, and that's called the Sudbury breccia or a pseudotachylite. And that's again another thing that's common for all big meteorite craters, is breccia in the base and shatter cones around the periphery for many miles. As well, the fallback breccia, which I don't have an example here, is always present with every meteorite impact. You get broken rock falling back in, and in this case, it was consolidated into a fallback breccia or swavite. Here are some conical fractures. You can see a hand there for scale. These are present in the rocks all around the Sudbury impact structure for miles. These are shatter cones in situ. So here's what the Sudbury structure looks like today. It doesn't really look like a meteorite impact structure like you might expect, but in fact, these are the sediments in the middle, the fallback, the Sudbury structure, and all the shatter cones. You can see them all around if you investigate the local rocks. Why does it look like this? There's a good reason. If we look back at that original structure, and I think probably it was a little deeper than this, but this gives you an idea of the 200-kilometer structure under the shallow sea at the time. This is what it looked like right after impact. But between 1.8 and 1.1 billion years ago, there was huge mountain building mountains very similar to the Rocky Mountains. And there's huge amount of thrust faulting, which deformed that structure. Imagine the nickel and copper deposits that were lost. And eventually it was eroded down to this level. And of course, that's what it looks like today. That's what really a 1.5 billion years of erosion can look like. Astonishing. So there's our present day Sudbury structure. It's torqued up at this end and squished and eroded. It used to be much bigger. And if you look carefully at this satellite, you'll see that exact shape exemplified, illustrated in the topographical forms of the land around Sudbury. This is Sudbury. Various mines around the edges. The mines are mostly around the edges. And this, coincidentally, is another meteorite impact over here. This is the Wanapitei crater with many of the same characteristics, but no ore bodies. For you geologists, the base of that crater is that layered impact melt sheet composed of various ultramafics and granite breccias where it smashed into the granite. It's the norite breccias hold the disseminated sulfides, and as well the norite hosts the massive or disseminated ore bodies. In the footwall embayments, right in the footwall, there are massive sulfide, more copper-rich, platinum group metal-rich bodies, which result in some pretty interesting minerals. I hope all my Sudbury friends are holding their tongues if I make any mistakes. This is my understanding of it, so I hope I'm mostly right. Okay, minerals. This is sort of the rough three-phase mineral paragenesis. The first minerals that formed that we find essentially a lot of them floating in the sulfides are things like ilmenite, magnetite, gersdorfite, sperrylite, pyrite. And later, when the sulfides, the mass of the sulfides consolidated, we got the pyrrhotite, pentlandite, chalcopyrite, cubanite, et cetera, and the important ore mineral pentlandite, all crystallizing as massive sulfides and disseminated sulfides. Later, many of these kind of minerals crystallized in lower temperature veins and other geological happenings. Some of the more interesting minerals. Okay, so we'll go alphabetically through the various minerals. Anthraxolite, or really a type of bitumen, is mainly found in those sediments in the center of the Sudbury structure, but also in some of the later veins with sulfides in the calcite. Here's a long aragonite crystal. At various times in various some of the mines, large vugs were found with interesting things like aragonite crystals. Not a lot were recovered, but over the years, some really good crystals have been recovered. The Sudbury structure is the type locality for arsenohashicornite. Probably many of you have never even heard or seen about an arsenohashicornite crystal before, but here's a really good example, an 11 millimeter crystal, well formed, and really a kind of a world-class crystal for that mineral. More often they're a bit more rounded, embedded in chalcopyrite and other sulfides. In some of the later stage veins, we get really nice crystals of calcite in many different forms. Some of them are these kind of mauvey colored crystals that we often see in sulfide deposits. I'm not sure why. Crystals like at Balmat and other places, we get beautiful mauvish crystals. Here's a couple, the next two are from the Beckett collection. This is a large, about 5-inch, beautiful 5-inch crystal of calcite with mauve tinting. And a little bigger again, a giant crystal from the Beckett collection from Falconbridge mine. Totally different habit. I think these kind of crystals often occurred with cubonite in some of these later stage veins. Very nice calcite crystals. It seems that good crystals occurred at every mine at different time periods, and some once in a while some were kept or salvaged, sometimes more than others. Chalcopyrite, despite being the most common copper mineral, rarely occurs in significant crystals. It occurs in rich footwall deposits at many of the mines, often with bornite like this, and millerite. Those are patches of millerite, but rarely in crystals. Here's a nice crystal, just a 10 millimeter crystal from the Arrington mine. Here's a nice crystal, small crystal from my collection from the Falconbridge mine, and some from the Strathcona. But that's it for chalcopyrite. However, like in Sweden, we get really nice cobaltite crystals embedded in the sulfides. Very similar habit and very similar looking to the Swedish crystals. Sharp cuboctahedra, usually embedded in chalcopyrite, pyrrhotite, pentlandite. That's about as big as I've seen them, 11 millimeters or so. This is more of a rarity. On occasion, dendritic copper is found near surface in fracture fillings, which perhaps is caused by some kind of reduction reaction in the oxidized zone. This is interesting. This is a piece a piece of core I got from Ed Debicki years ago that's been cut and polished. And if you look carefully, you'll see lamellar inclusions of cubonite in the chalcopyrite. At first glance, it just looks like chalcopyrite, but if you look carefully, these are lamellar inclusions of cubonite. And cubonite turns out to be actually in the overall mineralization of ore bodies, actually quite common, and it's probably mistaken for chalcopyrite a lot of the time. Another case in point, this is massive sulfides, slightly oxidized. So you see these kind of veins of darker mineral. Well, these are veins of cubonite, solid cubonite in the massive sulfides. If you look closely, see that little vug right there. See that tiny vug? If you look closely at that vug, you'll see, in fact, it's full of small cubonite crystals. Some people have estimated that possibly up to 30% of the copper in the Sudbury structures, in the Sudbury ore bodies, comes from cubonite and not chalcopyrite, which is, I think, pretty interesting. It does occur in wonderful crystals there. The Strathcona mine was a great example, a great place for cubonite crystals for a period of time. Here's a 20 millimeter crystal, just slightly twinned, from the Strathcona mine. This is in the Royal Ontario Museum collection. And this is even nicer. It's a very large 35 millimeter twinned cubonite crystal. It's not your cyclic twinning, but you can see the twin plane over here. It's just a simple twin. Again, from the ROM collection. At one time, I don't know if you remember, back in the mineralogical record 30 years ago, there was a fellow advertising cubonite crystals from the Strathcona mine for sale, and you could buy cubonite specimens for $20, $30 to $40, really nice ones at the time. There was lots. He had lots anyway. The Strathcona mine was the famous place for the cubonites in the Sudbury campus, as far as I know. Some of the later stage hydrothermal veins sported nice crystals of apophyllite. Here's one in my collection from the Craig mine. Just bladed tabular crystals. And here's another one from the Strathcona mine that Roger Poulan has in his collection. Excuse me. On occasion, they run into, in some of the north-south striking tension veins, they run into galena in the veins. Here's some from the Hardy mine, simple crystals. And here's some really bizarre ones from the Hardy mine. You can see they're actually almost like melted galena crystals coated with sphalerite, with pyrite. And that's from Roger's collection. Gersdorfite is relatively common, but not in big crystals. These are about, well, I shouldn't say these are the biggest ones I've seen, but maybe they get bigger. They're usually embedded in massive sulfides, and generally they're mostly just small crystals, like a couple of millimeters, but lots of them. In many of the ore bodies, you'll find zones of Gersdorfite crystals. On occasion, particularly at the Vermilion mine, you can find electrum, gold rich in silver, and many of us have found gold at the Vermilion mine. There's another example. It was, in fact, mined for precious metals, that Vermilion mine. This is a small place called the Norduna mine that I don't know its relationship, but it is in the structure, but I'm not sure of its relationship to the other mineralization in the structure. Sometimes marcasite is found in some of the late stage veining with quartz and calcite. Usually in faults and late stage veining. This is your typical millerite that we're all used to seeing. This is in a piece of diamond drill core that Joe D'Oliveira gave me years ago. Very nice needles of millerite with small chalcopyrite crystals. I'm not sure what the pink mineral is, but maybe zoisite or something. But you can get some really nice ones, particularly from the McLennan mine. It had excellent millerite sprays and crystals. Here's probably the best one I've seen. It's in Rod and Helen Tyson's collection. More impressively and more importantly, millerite occurs not just as fine acicular crystals, but as really gigantic cleavages, particularly in the footwall massive sulfides. So this is a good example that I got from Ed DeBicke years ago. And if you look at this carefully, you'll see the cleavage of this one crystal embedded in the sulfides is 18 centimeters across. Years ago, I never would have even conceived of millerite having cleavage like that. I think of it as just hairy little crystals. 240 millimeters across. It's quite something. That's the specimen. 18 centimeters of cleavage. Well, we find other arsenide minerals like nicoline, as well as the Gersdorfite, malachite, things like that. Pentlandite, I wish I had more examples of pentlandite to show you, but generally it just occurs as isolated crystals. They're often called pentlandite eyes in the massive sulfides, but that is the mineral that where pretty well all the nickel comes from in the Sudbury camp. Usually it looks like little several millimeter crystals embedded in pyrrhotite and chalcopyrite. Of course, pyrrhotite is the most prolific mineral, I think, in the entire deposit. There's so much pyrrhotite. At one time, they tried to take the pyrrhotite, roast it, and make iron out of it, make iron pellets for to recover the iron, but it just wasn't a commercially viable thing. Too much sulfur, too much acid, sulfuric acid. So they gave that up, but there's a lot of pyrrhotite in the Sudbury ores. Here's some examples. Sometimes it coarsely crystallizes in the massive sulfides. You can see rough hexagonal kind of shapes. Here's some nice crystals from Gil Benoit's collection. Unusual. In those footwall ore bodies I was telling you about, the precious metal rich ore bodies, sometimes there's masses of bornite with huge plates of native silver in them. Here's a couple of examples. This is in fact a giant plate of native silver. You can see the silver poking out here and there. That's coated with bornite. It's a 29, it's a foot across. And here's another one from the Beckett collection that's even bigger, 36.5 centimeters long. That's a plate of silver, a thick plate of silver coated with bornite. Quite a lot of this was recovered from some of the mines in the northwest part of the camp and was sold as specimens for years. And many people have these in their collections now, although mostly smaller than these. Sperrylite. This is probably the mineral that causes people the most excitement from the Sudbury area. It occurs as nice crystals in massive sulfides, particularly chalcopyrite. This is a Sperrylite crystal from the Frood mine, which is a little less common. We don't often see them from the Frood mine. Here's a beautiful 5 millimeter crystal from the Frood mine. The Vermilion mine is really the source of Sperrylite crystals. This is a fairly large 5 millimeter crystal from the Vermilion mine. This one's particularly interesting. It's a sharp crystal, cuboctahedron, but it's embedded in Millerite. You can see the cleavages of the Millerite. Four millimeter crystal. Sometimes it just occurs as grains in platinum-rich ores, and here's a good example from the Frood mine, with just all kinds of Sperrylite crystals embedded in the massive sulfides. However, the Broken Hammer mine, which is one of the most recent mines, it was a very small mine, largely mined for the precious metals in the north part of the Sudbury Basin, Sudbury structure. Beautiful Sperrylite crystals with mirror-like faces were recovered up to fairly large sizes. The Broken Hammer mine. Here's some good examples. These all say the Joyce, many of them say the Joyce collection, but in fact, many of them have been dispersed to other collections. And unfortunately, I didn't keep track of where they went to. I still have some of them. Beautiful Sperrylite crystals. Sometimes they're not embedded in sulfides. Strangely, they're embedded in silicates. This one's embedded in quartz and epidote. They're pretty attractive specimens, very interesting mineralogically. Not nice? And in some of the structures, particularly in the younger structures of the Sudbury structure, you can find there's a sphalerite crystals in some of the late stage veins. Okay, we're getting near to the end. I just want to have a little bit of an environmental postscript. Sudbury has a reputation for being a very ugly desert-like place, and that reputation unfortunately came honestly. For many decades, Sudbury was really heavily polluted by sulfur dioxide. The trees were cut for construction and roasting the ores and for underground mining, and the sulfur dioxide from smelting killed the remaining plants, which caused heavy erosion, resulting in bare hills, lowering the pH of surrounding lakes, sedimentation of the lakes. It was a mess for many years. But the mining companies, when they realized the error of their ways, egged on by governments and people, did something about it. This is what I'm talking about. This was the common practice years ago. They just piled up many feet of wood. This is all logs. And then you can see they had these giant stackers that stacked ore, massive sulfide ore on top of the wood. And then they just lit the wood on fire and let it sit there for a couple of months, roasting the ore to roast out a lot of the sulfur. And that sulfur dioxide just spread across the land. And you can see here the roasting piles, and the sulfur dioxide just drifted across the country and killed everything, caused the erosion, et cetera. And so Sudbury did resemble a moonscape for many decades. NASA actually sent moon astronauts to Sudbury for training, not because it looked like a moonscape, but for geological training. But people like to pretend they did it because it looked like the moon, but that's not why. They did it because of the all those structures we were talking about earlier, things they'd encounter on the moon. So the good news is Sudbury is very much cleaner and greener now. Billions and billions have been spent by the companies over the last several decades to reduce sulfur dioxide emissions down to almost zero. So back in the 60s, they built this super stack. It's called the super stack, and it was one of the largest freestanding structures in the world. And its sole purpose was to take the sulfur dioxide from the smelting process, put it way up in the atmosphere so it would be diluted as it drifted out into the world. And it worked. Sudbury started greening up immediately, but the sulfur dioxide still went out into the atmosphere. Over the decades, they've put billions into pollution control, scrubbing, acid production, and this stack now is obsolete and will be torn down because there's so little sulfur dioxide being emitted into the atmosphere around Sudbury. It's no longer needed, and Sudbury is greening up more every day. It's quite a beautiful place with many lakes, now pH neutral lakes all through the city, and beautiful greenery. That's a wonderful place to live. So I want to end with that positive note because a lot of people don't realize the changes. As well, the wealth that's been generated there over the decades has made Sudbury a center of mining technological innovation. I say mining, that includes geology, mineral processing, smelting, underground mining, etc. There's a fantastic university there now, a great community college. The old Creighton mine is home to the Creighton Neutrino Observatory, where atomic particle observations are carried out deep in the earth. As well, the Sudbury Science Center is a great attraction for tourists and students who want to learn about all kinds of science and environmental things. So Sudbury has turned out to be a great place that I was very proud to live in for a number of years and be associated with many times over the years in my business, my career in the mining industry. I'd like to thank Roger, who's not doing very well health-wise right now, for his great mineralogical and geological experience, which has taught me a lot of years and helped me put this presentation together. I'd also like to thank Joe D'Oliveira, Gil Benoit, Ed and Ruth Debicki, all of the Sudbury area. I'd like to thank Chuck O'Dale, who's a couple of his key sketches I stole to illustrate things in this, and Terry Wallace, who helped me with that. Thank you for putting up for my coarse voice for this presentation. Hopefully it didn't drive you too crazy. And that's the end. Thank you for listening and watching. I guess they'll turn off this recording, and if you have any questions, we'll try and answer them. Thank you very much.